Swayam Prabha. Digital India. Educated India.
So first let's dispose of this flow in a pipe problem. If you recall, we talked about a pipe of length L, a horizontal section of length L, cross-sectional area A equal to pi r squared, where r is the radius of the pipe. The water comes in here and goes out here. The inlet pressure is P1, the outlet pressure is P2, the atmospheric pressure. This is the pressure head here. P1 minus P2 is the difference in atmospheric pressure and the pressure head. Okay. And this length was L. We argued that the discharge rate Q, the volume of fluid coming out per unit time, was equal to pi r squared times the average velocity V in the pipe. But then I said that actually Q is proportional to r to the power 4, and that second power of r must come from here, the average velocity. Now the question is, the difficulty was that the answer is going to depend on L as well as r, and L over r is a dimensionless quantity. So you have two lengths in the problem, two quantities of dimension length in the problem, and you can multiply any answer by any function of the ratio of the two and the answer would not change. So it's ambiguous. That means dimensional analysis fails unless you use a trick. The trick is to break the problem up like this, pi r squared times the average value of V, and to recognize that the flow profile is going to look like this. It's going to be fastest in the center. The velocity is going to drop off as you go towards the edges till it is 0 at the ends here. If you actually plotted the profile itself using hydrodynamics, it turns out to be a profile like this. Maximum velocity speed here, minimum speed here, 0 in fact, there's viscosity. But we are not going to do that, we are not going to do hydrodynamics. We are going to argue that V equal to a function. What are the quantities it can be a function of? Well, it's going to be a function of R definitely, because the narrower the pipe, the faster it's going to come out. So the average velocity is going to be a function of R. It's going to be a function of the viscosity of the medium. So that's what causes the average to, the velocity to change across the cross section. And it is going to be proportional not to L, but the pressure gradient, the rate in which the pressure changes across this pipe. So it's going to be proportional to delta P over L, where delta P is P1 minus P2. So it's not proportional directly to L, but rather inversely proportional to L, because it's a proportional actually to the rate of change of pressure with respect to the length, the pressure gradient. So now use V equal to R to the power alpha, eta to the power beta, delta P over L to the power gamma. Solve for alpha, beta, gamma. Then you get an expression for V. You put that in here and you will end up with this being proportional to, there is an R to the power 4, there is a delta P over eta L times some constant, numerical constant. For a circular pipe with stick boundary conditions, as they call it here, this factor turns out to be E6 pi. But that you can't get from numerical analysis of this kind. So that's how this dimensional analysis can be used in this problem, provided one puts some physical input into it. Here the key was that you recognize that the flow is proportional to the pressure gradient rather than the pressure itself, the rate at which the pressure changes. Similarly, for problems of this kind, when you have too many parameters, too many variables, you have to reduce the number of variables by physical arguments. Let me give a classic illustration of this in a very trivial way. You're familiar that if you took a simple pendulum of length L, bob mass m, length L, and it's oscillating back and forth in simple harmonic motion, the time period is equal to what? 2 pi root of L over G for small oscillations. The way you derive this is by arguing that the time period is proportional to L to the power alpha, m to the power beta, little g to the power gamma. You have three equations and three unknowns, and you can calculate what these exponents are. That's the standard way. But now I come along and say that you cannot say that t is the function of m and g alone. What about other fundamental constants? What about c? What about Planck's constant? What about capital G? These are, after all, fundamental constants. Why should they not appear in the formula? Now you have 6 unknowns and 3 equations for ML and T coefficients, and you can't solve the problem.
Where there is 6 unknowns, we can find m in terms of the other constants.
What? No, I'm going to say that ab initio, I don't know anything about this, but ab initio, it looks to me as if the answer is a function of all these parameters, including these fundamental constants. Why should they not appear? Then you have 6 powers to find and you have only 3 equations. So what? So what? Like the Planck length depended on c to the power 5 square root and things like that. Yes. Capital G is not needed anymore. Little g, after all, is capital G divided by mass of Earth divided by radius squared and so on. So this is not there. Same goes for what? Oh, I might as well know. In fact, I'll make it worse. Also, Boltzmann's constant.
Sir, we can't use dimensional analysis because we have more than 3 constants.
Yes, you have 7 of them, and one of them he eliminated by saying capital G is the same as little g. So little g is just capital G, capital M over R squared. Agreed. Agreed fully. Because the pendulum's length is small compared to the radius of the Earth, so it's just all small oscillations. I'm working at fixed temperature. Temperature doesn't play a role here. There's no exchange of heat energy between the pendulum and anything else. So there's no K Boltzmann. I'm looking at non-relativistic motion, so there's no C. I'm looking at classical physics, not quantum mechanics, so there's no Planck's function. Then you can do your little 10 standard exercise and get square root of L by G. You still can't get the 2 pi. Okay? So some physical input has to go in. Just as it was the pressure gradient rather than the pressure itself. It made a difference here. You can't solve all problems by dimensional analysis. They're not all that cheap. But where it's applicable, especially in fluid dynamics, you use a lot of it, but you have to supplement it with arguments like the one I've given. Okay, now let's turn to a different topic altogether.
Sir, I have a question.
Yeah, please.
Sir, we can, by dimensional analysis, we can find the relation of LG with respect to T, but how do we find out the constant in every dimensional analysis question?
You can't.
Is that only found out experimentally?
Yeah. Or some theory or some fundamental derivation. Writing down equations of motion, writing down the laws of hydrodynamics. This flow, this kind of flow, by the way, is not turbulent flow. This kind of flow is called Posey flow. And you write down an equation of hydrodynamics called for the fluid element, it's the equation of motion for a fluid element, the analog of Newton's equation. It's called the Navier-Stokes equation. You have to write that down and try to solve it with boundary conditions. That's how you get the 6 pi factor. Because what happens is, if you take another example, if you take a ball, a metal ball, and drop it inside a fluid of some viscosity, this ball travels downwards and sinks under this flow under gravity. Then it turns out that the terminal velocity mg is given by 6 pi a theta. And the 6 pi comes by saying that the instantaneous velocity of a fluid element touching this ball is 0 because of viscosity. It's called a stick boundary condition. On the other hand, if this was a superfluid, for example, then there'd be no viscosity. This would just sink straight down. It would be a slip boundary condition. This will become a 4 pi. If this were an ellipsoid instead of a sphere, it becomes some other factor and so on. For simple geometries, you can compute this factor. But that can't be done with dimensional analysis. Anything else?
In Stokes' law, we use the constant 6 pi, right? 6 pi a beta t.
Yeah, what about it?
So why is that applied only for a spherical object?
Well, you have to say how the fluid moves, right? And for that, you have to specify what happens at the boundary of the fluid and the solid interface. You have to make an assumption about the instantaneous velocity on that boundary. And then you have different kinds of boundary conditions. Either it slips past the fluid solid, or it sticks to it and slips past with some friction, and so on. And the constant changes. That 6 pi is not a very trivial thing to derive. It's fairly complicated.
So we get different constants
So
for different.
we may get different.
Yeah, for different shapes, you'll get different constants. If it's a bacterium falling down with legs or whatever, pseudopods, it'll be a different constant. Since you mentioned that, let me give a reference here. There's I'm trying to remember the name of the author, by Berg. And it's called Random Walks in Biology. And he talks about what happens when bacteria drop, when ellipsoids drop, etc., etc. It's a sort of amusing little book. Old book. Any other questions? Because I'm going to turn to some other thing, totally different topic. Unless you have some other questions. Oh, one small slight digression. Since we were talking about rest mass and so on this morning, let me tell you what relativity says. A lot of the mystery of special relativity is knocked out if you know the correct relation between the energy and momentum of a particle in free space. Turns out, relativistically, non-relativistically, you write the total energy of a particle as kinetic energy, which is 1/2 p squared over m. P is mv, plus the potential energy. For a free particle, there's no potential energy, it's p squared over 2m. That's the energy. The actual relation between the energy and mass and momentum of a free particle in relativistic physics is this. And I'm not going to derive it, but it's this. So it's a quadratic relation between energy and momentum. And if you plot one against the other, E is positive, being the total energy, and this is P. Okay. What does this curve look like? It's part of a parabola? Parabola means this is quadratic also. So it's of the form y squared minus x squared equal to a positive constant. It's a hyperbola. It's a hyperbola. It's a rectangular hyperbola. So asymptotically, when P is much larger than, when this is much bigger than that, E is Cp approximately. So this line is E equal to Cp. When this term is comparable to that term, in fact, when P is 0, E is m naught C squared. So it starts here. It's called the rest energy at 0 momentum, and then it asymptotically approaches E equal to Cp. For a photon, m naught is 0, E equal to Cp. You already know that formula. Did you know that formula? Pardon me? E equal to? Again, that's a very historically unfortunate equation because it's a wrong equation. It means something, but it's not, it's misleading. You know the formula E equal to Cp for a photon. The energy is linearly proportional to the momentum for a photon in magnitude. You're familiar with this formula? Yes or no? No? You know it in another form, except you don't know that you know it. By the Einstein relation, E is h nu and P is h by lambda by the de Broglie relation. So what this equation is saying is that nu lambda equal to C. The speed of the wave is its frequency multiplied by its wavelength. That you know. The particle version of this wave relation is E equal to Cp.
Since photons don't have mass, I'm not understanding how can we have.
How can I have what? Yeah, so photons correspond to putting m naught equal to 0 in this formula. Then E squared is C squared P squared or E equal to Cp. This relation is true asymptotically even if there is a mass here because P is much bigger than this. This term is much bigger than that. So if you're asked what's a non-relativistic approximation to this, the relativistic limit, it's when this becomes bigger than that, then it's ultra-relativistic. And if m naught is 0, this term is always bigger than that. So photons satisfy this line. Massive particles satisfy this line with the rest mass. So does this particle have a characteristic momentum that I can say that if it's lower than that, it's non-relativistic, if it's much lower, if it's much higher than that, it's relativistic and so on. Can I say that? Is there a typical momentum in the problem? From m naught and C, can you find a momentum?
MC, right?
M naught C.
Yes, sir, M0C.
M naught C is the dimensions of linear momentum. What do you call M naught C? What do you call H over M naught C? What do you call? There's a name for it. M naught C has the physical dimensions of a linear momentum, mass times velocity speed. What do you call this momentum? What do you call this momentum? That's a length. What do you call this length? What wavelength? No, de Broglie wavelength is h over lambda. Lambda is h over p. What is this? This is the characteristic momentum. This is h here. That has dimensions of a length. What length is it? It's like the size of the particle, if you like, the extent of the particle. It's called the Compton wavelength. It's the so-called Compton wavelength. So coming back to this formula, now look at what happens if I put. So I have a momentum, and if P is much less than m naught C, I say it's non-relativistic. P comparable to or greater than m naught C, relativistic, and P much greater than m naught C would be ultra relativistic. Let's look at the non-relativistic limit properly, and then you'll understand where non-relativistic physics fits in. In this regime, this term is very small compared to that. So I take out an m naught c squared. So c squared cancels. So coming back here, that's an exact relation. All I've done is to take out this factor m naught squared c squared outside, and this is it. But if p squared is much smaller than m naught squared c squared, this is a small correction to 1. And then you got to add it and take a square root of the whole thing. What would I do next? I have this, I want a systematic expansion in P over M naught C. What would I do?
Approximate the small correction to be 0 and then just take that one.
What result in algebra do I use in order to expand this in a power in P over M naught C? The binomial theorem for fractional index. So what's the first term? What's the next term? The 1 is here. 1 plus x to the power half. 1 plus half x. Plus next term. Half times half minus 1 over 2 factorial. So that's minus 1/8, the square of this whole thing. What does that become? First term is m naught c squared, that's this term, plus, what's the next term? A term which is proportional to something, something, something divided by c squared plus h. What is this called? It's the energy in the absence of any motion of the particle when P naught is 0, when P is 0. What do you call the energy when the particle is at rest? What do I call it? What energy? Potential energy. There's no, it's a free particle.
Rest energy?
Rest energy. Yeah. Scientists are very literal people. It's called the rest energy. Mass and energy are equivalent because of this. When a hydrogen atom or atom bomb explodes, some rest energy is converted into energy. This is not present in non-relativistic physics because particles cannot be created or destroyed in non-relativistic physics. Whereas in relativistic physics, that regime, matter and energy are interconvertible. That's why when you shoot two protons at each other in the Large Hadron Collider, thousands of particles come out. They were created at the instant of collision. So the first term is the rest energy and is irrelevant for non-relativistic physics because it's always there in the ledger. input and output, and is ignored completely. What's the second term?
E square by 2m.
And what does that remind you of? Exactly. Now the reason, you know where the formula half p squared over 2m comes from now. Comes from here. What is great about that term? What's striking about that term? This is why we were able to do physics before Einstein. If that term had not been present, it had been present in a different way, we wouldn't have been able to do any physics at all without modern instruments. It doesn't depend on c. In Newtonian physics, c is infinite. The speed of light is infinite. In classical Newtonian physics, the speed of light is infinite and Planck's constant is set equal to 0. Then you get the whole of Newtonian mechanics. So it was damn lucky for us that this term does not depend on the speed of light. So you could deal with objects which are moving much slower than light, otherwise you would have had trouble. Sometimes the universe is very kind to us, as in this case. Okay. So now you see where the rest energy comes from, where the normal non-relativistic kinetic energy comes from, etc. But there are corrections to it. These are the corrections. This is the exact formula. Okay. What this also means simultaneously is that just as the relation between energy and momentum is not the non-relativistic one, the relation between energy and momentum and velocity is also not linear. The momentum of a particle of rest mass m at momentum p is given by m naught v. So the formula P equal to mv is again a non-relativistic formula. Should really have been P equal to m naught v, but okay. What does this look like as a graph? Let's plot the magnitude v versus the magnitude p. What does it look like? The magnitude of this vector is the magnitude of this vector m naught v, the speed divided by 1 minus v. What does this curve look like? When v is much smaller than c, this is c, say, the v axis, this is the point c. When v is much smaller than c, this can be neglected. Second order term. Then p is m naught v. There's a linear relation. So the relation goes like that. This is the non-relativistic regime. What happens when v is equal to c? It becomes infinite. So this curve goes up like this, but after a while it becomes non-linear and asymptotically tends to infinity, as v tends to c. Now the mystery as to why v cannot become bigger than c is explained, because when v reaches c, p becomes infinite. And you can't have anything bigger than infinity. Okay. So this nonlinear relation is what is responsible for this behavior. You can also ask, what is E? What does the energy become? By using that quadratic formula and plugging this in for the first term. Then verify this. That's what the energy turns out to be as a function of V. We already plotted E versus P, but now let's plot E versus V. And here is C. When V is 0, it's just the rest energy here, m naught c squared. And when V becomes C, it blows up. That explains why you can't exceed C, because you need infinite energy to do that. Now, unfortunately for us, Einstein started this and then it was perpetuated by other people. Einstein knew what he was talking about. Sometimes this quantity here has the dimensions of a mass. This is dimensionless, V over C, and this is a dimension of mass. So it is convenient to write this in the form mc squared, defining m as m naught over square root of whatever. So what one does is to write this as equal to mc squared, where m is identically equal to m naught over square root of 1 minus b squared over c squared. So you call m the kinetic mass because it depends on the velocity. And then that explains the formula E equal to mc squared. But you agree that it's just an algebraic substitution, definition of m. I see no virtue at all in defining a thing called the kinetic mass, because it gives students a wrong impression that mass increases with velocity. The particle somehow becomes fatter and fatter till it becomes infinitely fat at b equal to c. Not true. There's only one mass and that's the rest mass. And in modern books, the symbol m equal to m naught over this is not used at all. They just use the symbol m for m naught, because the particle has only one unique mass and that's its rest mass. The so-called kinetic mass is a myth. Yeah.
So how did we arrive at this correction square root of 1 minus e squared by
We started with E squared equal to C squared P squared plus m naught squared C4. We started with that, right?
Yes.
Okay. Now the way to write this formula, this comes from the fact that you should write this formula as m naught squared as E squared over C squared minus no, sorry. Write it in this fashion. Then it turns out that in relativistic physics, just as in normal physics, in non-relativistic physics, you have scalars and you have vectors under rotations of the coordinate axis. Under so-called Lorentz transformations, you have quantities called 4 vectors. So the combination E over C and P acts like what is called a 4-dimensional momentum P, a relativistic momentum P. And then the scalar product of P with P, E dot P, is precisely this quantity. So it's invariant under Lorentz transformations. This comes from the recognition of the fact that space and time are mixed up. Similarly, energy and momentum are mixed up. Energy divided by C and momentum are mixed up. They form the 4 components of a 4-dimensional vector in Lorentz space. And the scalar associated with it can be 0 or positive, and this is the positive part of it. So it comes from here. As to why this is the simplest invariant, you need to know this 4-dimensional geometry. Right. Okay. So there's a perfectly rational derivation of it. Yeah.
So there was something about time being the fourth dimension. Is that actually true, or what is it?
That's again a sort of misleading statement once again. It's not a 4th dimension in the sense of a spatial dimension. It is more the fact that space and time are combined to each other with each other in relativistic transformations like the Lorentz transformation from one inertial frame to another. So that mixing up of space and time was what led people to call it as, fourth dimension. So just the analog of this relation here is that CT and P and R, position vector R, form a 4-dimensional coordinate, space-time coordinate denoted by X, for instance. So rather than saying that time is the 4th dimension, one really says that space-time is 3 spatial dimensions and 1 time dimension. So it's 3, 1. It's not a 4-dimensional Euclidean manifold, but a Minkowski manifold, 3, 1. 3 spatial dimensions and 1 time-like dimension. Again, the way it's established is by writing the so-called interval and the formula for it and so on. It gets technical. Okay. So time is not like space at all. It's very different from space. But space and time are combined. And the whole thing happens because of Einstein's postulate. So special relativity as a postulate, a physical postulate first made by Einstein clearly, and that says that the speed of light is independent of the velocity of the observer or the source. Okay, which means that what looks like, okay, let me even digress a little bit and say it. Suppose in my coordinate system, I have a coordinate system. At t equal to 0, according to my clock, I set off a spherical pulse of light. So here's my origin of coordinates. At t equal to 0, I flash a beam of light in all directions in space. So it propagates out in spherical waves. And at some time t, after the start, the wavefront will be out here. And the radius of this wavefront will be r equal to ct. Because speed is c for this wavefront, and in time t in my frame it goes up to a distance ct and in all directions about the origin. Spherical waves. At a later time it would be a wave like this. It will propagate outwards in all directions in concentric circles, spheres. Suppose this is looked at by an observer, a moving observer who started with me at the origin when I flashed the light and then started walking in this direction at a speed v. What is he going to see? Well, at some wavelength, it doesn't matter. Doppler shift changes the frequency, but it doesn't matter. What about the wavefront itself? What will he see? If it were a sound wave, he'd see this. He'd see foreshortened waves in the direction in which he moves. Let me draw that more clearly. As he moves along this, he would see this is foreshortened nearer and nearer in this direction because he's got a velocity v. What speed would he see for that light? C minus v. But then the postulate says it should be the same in all frames of reference. That was the big postulate he made. By the way, if he sees a foreshortened wave like this, suppose he were able to exceed the speed of the wave, what would he see? Imagine this is sound. Then he would see something, when he crashes the sonic barrier, he would see something like this. Once he smashes the sonic barrier, he would see something like this. He would see a shock wave will depart from him. Right? Now, he doesn't travel faster than light, so this is ruled out. But he would see something like this if light added, the velocity added in the same way as a moving frame, as sound does. But that's not possible. He's got to see exactly the same spherical waves as before, the same shape, right? In other words, just as in this frame, c squared t squared minus r squared is 0. For the other observer, he would see c squared t prime squared minus r prime squared equal to 0. Also spheres. There are two sets of solutions to this. Till Einstein came along, people recognized only one set. And that set is r equal to ct. R prime equal to r. T prime equal to t. Time flows exactly the same for all observers. Einstein came along and said, no, there's another solution to it. And that mixes up t and r. Those are the Lorentz transformations. Now you see why Lorentz transformations, where they come from. From the postulate of relativity. Because if light has to travel again in spherical waves exactly the same speed as in the previous frame, then R prime must be Ct prime. In Newtonian physics, T equal to T prime, then R is compelled to be R prime.
So, but when we take it numerically, the postulate doesn't make sense. Like if we take the speed of light to degree with FR,
Yeah.
how does the postulate make any sense physically?
Why?
Like if point is special relativity.
How does it matter what the value, numerical value is? You're saying there's an entity which travels at a speed which is independent of the state of motion of the observer. So spherical, concentric spherical wave should be the same in all frames. Your intuition is wrong because normal our intuition is, let me clarify this. Suppose I have a frame of reference, me, observer 1, sitting here. Another observer is sitting on top of this origin at t equal to 0 and starts moving in this direction with speed v1 with respect to me. So this observer O2 moves along my x-axis with speed v1 with respect to me. And let's suppose there is a third observer who also coincided at t equal to 0 and moves with speed v2 with respect to this guy O1. Sorry, O1, O2, O3. So O2 moves with speed v1 with respect to O1. O3 moves with speed v2 with respect to O2. What is the speed of O3 with respect to O1? In normal physics, non-relativistic. V1 plus V2 because it's moving quite. So the resultant speed V this guy is already moving at speed V1 and this fellow is moving at speed V2 with respect to this. So with respect to me is moving at speed V1 plus V2. Right? Yes? But the correct law of addition of velocities, just as the correct law of addition of the law of which we had for the energy momentum, the correct law is this. So it's V1, V2, 1 plus V1, V2 over Vc squared in the denominator. That's the right law of addition of velocities. So you can start the whole of special relativity, you can derive the whole of special relativity by taking this to be the law of addition of velocities. That's the right law. But now look at what happens if V2 is C. What do you get if one of them becomes C? V becomes C once again. That shows that the speed of light is independent of the velocity of the observer. So one way of saying it is that what special relativity does is to modify the law of addition of velocities by this formula. Yeah.
So in the earlier case you gave, sir, if a body is putting out 2 photons, one on either side, and then so it will have the same energy, right? If you have 2 photons of the same energy being emitted on 2 sides, so like a circle, and then a moving observer comes by, he will see the shifted photons where one of them is more shifted than the other frequency. Then won't the energy be different from his frame of each photon?
The energy is not the same in all frames of reference. The energy transforms like the time component of a 4-dimensional vector, so it very much changes from one frame to another. That's true even in non-relativistic physics. This object is at rest with respect to me, its kinetic energy is 0. If I move with respect to it, it appears to move in the opposite direction and its kinetic energy is non-zero for me. Right? So the energy is not a scalar, it's the time component of a 4-dimensional vector. Yeah.
So how was this experimentally verified?
Over the last 125 years, millions of experiments have been done on the consequences of special relativity. and they've all verified it in its range of applicability. How do now we're talking about, you will learn about this in something called the Michelson interferometer. The Michelson interferometer measures the speed of light. You learn that in physical optics. I could describe it, but there's not enough time to do that. We'll talk about it.
So how exactly does it become independent of the speed of light? Can you please repeat that, sir?
How does the speed of light become independent of the state of motion of the source or observer? That's the postulate. That's the most concise way of writing the postulate of special relativity.
How is it proved, sir?
How is it proved, sir?
How is it proved?
How is it true? Its consequences are true. So you have a theory, you deduce its predictions, and if they are true, then this is true also. Okay. So you're asking, what are the tests of special relativity? What are the consequences that can be tested? A lot of them are tested. For instance, one of them is that the particle and its antiparticle must have the same rest mass. If it's an unstable particle, the particle and its antiparticle must have the same lifetime. These are all tested to some accuracy. You can ask me, how do I know the speed of the mass of a photon is zero? I don't know. I don't know anything is zero physically. I can only put bounds on it. I can only say it's smaller than such and such a number. Theoretically, it's zero. It's consistent with all our theories and predictions. But experimentally, the mass of a photon is known to be less than 10 to the minus 61 kilos. That's 30 orders of magnitude less than the mass of an electron. At no stage will we be able to say it's exactly zero experimentally. You can only put a bound on it. But its consequences can be tested.
Isn't the mass of photon zero, sir?
Yeah, the mass of a rest mass of a photon is zero. One of the consequences is that in electrostatics, Coulomb's law applies. The 1 over r squared force applies. That will be modified if the mass of the photon had a rest mass. It will be exponentially cut off. So we can test Coulomb's law to some degree of accuracy.
So where did 10 to the power minus 61? Where did 10 to the power minus 61 come from, sir?
Which test gives it? A combination of tests gives that limit. One of them is measuring intergalactic magnetic fields. Another one is measuring the magnetic field of the Earth from an artificial satellite. The third one is finding the resonant frequency of an LC tank circuit. There are tabletop experiments. There's a whole host of experiments.
Sir, if we know how that device works, which measures speed of light, will we be able to answer the question that, like, sir, have we been able to reach speeds comparable to speed of light?
Yes, for elementary particles. The photons in the LHC, the protons are traveling at 0.9999% of the speed of light. Maximum. Not infinite. Not at the speed of light, but infinitesimally close to it. Okay. The energy is in tera electron volts. The rest mass of a photon is 1 giga electron volt. And it's got a kinetic energy which is equal to 7 tera electron volts. So you can imagine how relativistic it is. Totally dominates. I think it's time for the next lecture.
Can I have a request?
Sure.
Can we repeat this lecture on special relativity sometime later when we have a greater understanding of the topics?
Sure.
And not
Yeah.
after lunch.
So because I felt like I understood parts of this, but I also didn't understand other parts of it. I would like to research more and get to understand this better.
Sure, sure. Yeah, I agree. After lunch increases the rest mass. So. Okay, thank you.
Thank you, sir.
Shri Gurubhyo Namaha. I take immense pleasure in thanking Professor Balakrishnan for his enlightening and eye-opening lecture interconnecting various concepts of physics and presenting it in an understandable format towards the 11th graders. I would also like to thank you, sir, for clarifying our doubts with curiosity and kindling our scientific temperament. Today, after these 2 lectures, we have lots to take back with us, sir. Once again, thank you, sir.
You're welcome.
Swayam Prabha. Digital India. Educated India.